In this video we'll be looking at half-life. If you're new to radioactivity, you might want to check out the first video in the series and then come back to this one. Remember, in the last video we said that the nuclei of certain atoms of certain substances can give out radioactivity. They can fire out alpha particles, beta particles or gamma rays. So imagine we have a substance here that's radioactive. I've drawn 16 atoms. Now of course in reality there would be billions upon billions of these atoms. Now the nuclei of these atoms can emit radiation, but there's no way for us to predict which one will give out the radiation first. Will it be this one that fires out the alpha particle first? Or will it be this one or this one? The point is we don't know because radioactivity is in fact random. What is important to realise, however, is that different radioactive substances decay at vastly different rates. Some radioactive substances, 90% of all of these nuclei here will decay within a space of time less than a second. With other substances, maybe only 20% of them will decay in thousands of years. There's a huge range of them. Half-life is about trying to make sense of that range. The half-life of a substance is the time it takes for half the number of nuclei to decay. A more precise definition is it is the time needed for the number of undecayed nuclei to fall by half. Take a look at this graph. This is the sort of graph that scientists would use if they were studying radioactivity. On the y-axis here we've got the number of undecayed nuclei. In other words, the number of nuclei that have not yet given off an alpha, a beta or gamma radiation. It started out at 1,000, and as time went on, we've got time on the x-axis here, we can see that that number went down as more and more particles gave off radiation. So this tells us which ones have not yet given off radiation. Now look at the numbers. We started out with 1,000. Let's see how long it takes for that number 1,000 to drop to 500. That would be one half-life. So if we go to 500 here and we move across, we will find that it took approximately, let's say about 4.2 hours. So the half-life of this substance, the time it took to go from 1,000 down to 500, would be approximately 4.2 hours. Now, the interesting thing about half-life is that that relationship continues throughout the graph. Let's try another half-life. Let's go from 500 here down to 250, which is somewhere here. If we go to 250 and we move across, we will find that it takes approximately about 8.5 or 8.4 hours. Can you see that that is two half-lives? From 1,000 to 500, it took approximately 4.2 hours. To go another half-life down to 250, that takes about 8.4 hours. Let's try that again. If we go from 250 down to 125, we would expect that to be about 12 something. So if we move the cursor across there, it hits the graph there at about 12 or 13 something. So it's approximately 3 half-lives. So it's important to understand that this relationship continues. The graph will halve its value every half-life. In this particular case, it was every 4.2 hours approximately. One big problem with that graph is that in real life it's actually very, very difficult to count the number of nuclei. There are billions upon billions of them and they're very, very small. So it's difficult to count nuclei. However, we do know that the amount of radiation given off, in other words the level of radioactivity, is directly proportional to the number of undecayed nuclei. So the level of radioactivity, in other words how much activity we're getting every second, is proportional to the number of undecayed nuclei. Counting the number of undecayed nuclei is very, very difficult, but measuring the level of radioactivity is very, very easy. So rather than drawing a graph of the number of undecayed nuclei, most scientists instead will measure the radioactivity and see how that changes over time, because if that falls over time, that means the number of undecayed nuclei is also falling over time. So we can calculate the half-life by looking at the activity and not necessarily having to look at the number of undecayed nuclei. This would be a more typical graph that scientists would draw. Let's have a look at the axes. So the level of radioactivity has been measured. Now it's measured in a unit called becquerels. Don't worry about that for now. But basically that tells us about how many decays we're getting every second. So it starts out, right at the beginning of this experiment, we were getting a figure of 5,000 for the level of radioactivity. And over time that fell, as you can see. So let's look at half-life again. We started out with an activity of 5,000. After one half-life, we would expect that activity to go down to 2,500 because we would expect the number of undecayed particles to have fallen by half, so the level of activity should fall by half. So if we go from 5,000 to 2,500, approximately here, and we go across and we hit the graph here, we find out that yet again it's about 4.2 hours. So the half-life is 4.2 hours, whether we measure level of radioactivity or whether we measure the actual number of undecayed nuclei. We can try that again from 2,500. We can go down to about 1,250. Now, of course, it's very approximate on this graph. And we get here and it is about 8 point something, which is what we would expect. So remember, when you're measuring half-life, you can either measure the number of undecayed nuclei, but that's very difficult, or you can measure the level of radioactivity, which is much easier. And when the number falls by half, that equals one half-life. Half-life is very unusual then in that it has two definitions. Both of them are equivalent. It does not matter which one you use. The first one we started with was that half-life is the time taken for the number of undecayed nuclei to fall by half. The second definition is half-life is the time taken for the level of radioactivity, sometimes people just refer to it as activity, to fall by half. Both of those definitions are valid. It does not matter which one you use. That's about it for half-life. Please do consider checking out the other videos. There are videos on almost every aspect of GCSE physics, and please also do subscribe to Physics with Mr. Drew.